Okay, so first, first we need to know that matter. We need to know that anything is supposed to be made up of, matter is supposed to be anything that's made up of particles that basically has mass and takes up space. So we need to know that, right, matter can be in the form of a solid, a liquid, or a gas. Okay, so for all types of matter, we need to know that matter is going to have physical properties. So we need to know that physical properties are supposed to be a trait of matter that can be observed without measuring or changing the chemical composition of matter. Okay, so right for physical properties, we need to know that physical properties, they do not involve a chemical reaction. Okay, so there are a lot of physical properties. Okay, so for example, color would be an example of a physical property. And then texture would be an example of a physical property. Temperature is an example of a physical property. Okay, temperature is also a physical property. Temperature is supposed to be the measure of average kinetic energy. In other words, the energy of motion of particles of a substance. Okay, so we need to know that basically um, temperature is basically supposed to be how fast the particles are moving. Okay. Okay. And then there actually is a difference between temperature and heat. So basically, temperature is supposed to be the average kinetic energy, but heat is totally different. Okay, so we need to know that but like heat is supposed to actually be a total amount of energy. Okay, so right, heat is supposed to be the total amount of kinetic energy. Temperature is the average amount of kinetic energy. Okay, so for example, if you have maybe like a teacup versus a bathtub, they could both be at the same temperature, like the water inside them could both be at the same temperature. Okay, but if you think about it, if you added up all of the particles inside the teacup, then let's say that maybe added up to 80 kilojoules. Okay, so and that's because basically the bathtub has a lot more molecules in it. So if you added up the amount of energy of each of the molecules in the bathtub, I mean, obviously because the bathtub has way more molecules, the sum total of the amount of energy and heat is going to be the same. Or I'm sorry, the amount of heat in the bathtub is going to be way, way more. Okay. But anyway, either way, temperature and heat are both um, physical properties. And then mass is also a physical property. It's supposed to be the amount of matter in an object. And it's usually supposed to be in grams or kilograms. And we need to know that for mass, there actually is a difference between mass and weight. So first of all, weight depends. Mass does not. Okay, so for example, a ball has a mass of 100 grams. The weight of the ball on Earth could be 0.22 pounds. Weight of the ball on Jupiter is 88 pounds. Weight of the ball on the moon is 0.17 pounds. But yet the mass is actually going to stay the same. Mass is 100 grams. Mass is 100 grams. Mass is 100 grams. Okay, and that's because basically the only difference is the gravitational pull. Okay, so we need, right, basically because Jupiter has a gravitational pull that's a lot stronger than the Earth. Then that's what results in the higher weight. But the mass, the amount of stuff in the object is staying the same. Okay, now for volume. Basically, right, volume is supposed to be the amount of space that an object occupies, and it can be measured in milliliters, liters, centimeters cubed, meters cubed, etc. Okay. We need to know that milliliters and liters are both used for liquids and gases. Centimeters cubed and meters cubed, those are used for solids. Okay. Right. We also need to know how to find the volume of an object with a very irregular, unusual shape. So like the volume of a rock, the volume of a statue or a little figurine. Just any object that has a really strange shape. Okay, so let's say this, we would need a graduated cylinder. So for a graduated cylinder, we would fill the graduated cylinder with a known amount of water. Okay, so first let me finish the graduated cylinder, 12. Okay, so let's say that we fill the graduated cylinder here. First of all, we need to know that this curve is called the meniscus. And you always read from the bottom of the curve. You never, ever read from the sides. So, okay, so basically the volume it looks like is about 12 milliliters. So let's say we have our rock. What we're going to do is we're going to drop the rock into the graduated cylinder. And common sense is going to tell us that the water level in the graduated cylinder is going to go up. So let's say it goes up to about here. Maybe let's just go ahead and make it about 20 milliliters. So that way when we read from the bottom of the curve, it's at 20 milliliters. Okay. Right. So basically the volume of the rock is going to be the difference in the volume of water. So because the water level rose 8 milliliters, then that's the volume of the rock, basically. Or actually, let me undo this for a second and let me put volume of rock. Okay, so 20 milliliters minus 12 milliliters, 8 milliliters. So, and that's close to the volume of the rock. But the problem is that the rock is a solid. And solids are supposed to be measured with centimeters cubed or meters cubed, not milliliters. So we would need to know that 1 milliliter is the same thing as 1 centimeter cubed. Okay. So right, that's the volume of the rock. Um, so right, basically the volume of the rock is 8 centimeters cubed. And we also need to know the reason why that this works. So we need to know that it's actually because of a property of water called water displacement. So water displacement is saying that basically the volume of water that an object kind of like pushes or shoves out of its way is equal to the object's own volume. So basically, because the rock pushed 8 milliliters of water out of the way, its volume is 8, the volume of the rock is 8 centimeters cubed. That's why, is because since it pushed 8 milliliters, then that means that it's equal to that same volume. Okay. Okay. And then let's take a look. So basically for right, volume is also still a physical property. And then density is another physical property. So density is supposed to be the ratio of mass to volume, and it reflects the degree of packing of particles in material. Okay, so we need to know that it's supposed to be density equals mass divided by volume. We definitely do need to know that formula. This means that things with high densities, that means that they have a large mass, but a small volume. So the particles are very heavy, but they don't take up very much space. And then things with low density, they have a small mass, but a large volume. Okay, so right, the particles are not very heavy, but they take up a huge amount of space. An example of a substance with high density would be a metal. Right, because the particles in the metal, they're very heavy, but they're very, very tightly packed, and so they don't take up very much space. And then for low density, an example of something with a low density would be gases. Because the particles of gases, they're very, very small. They have very, very little mass to them at all. But the particles spread out and can take up a huge amount of space. So they take up a large volume. Okay, now there is a little memory trick that we can use. So first of all, we have DMV. So this bar means division, and then this bar means multiplication. Okay, so what the way that you use this triangle is you just cover up whatever it is you're looking for. So if you're looking for density, you cover that up. You can basically hide that. And then the formula is mass divided by volume. Okay, then basically then you also cover, or like if you're looking for volume, you cover that up. And then the formula is mass divided by density. Okay, but then if we're looking for or if we're looking for mass, we just cover that up. and then it's density times volume. Okay, now let's take a look at luster. So either way, density also is still a physical property. Everything we've done so far is still physical because you don't need a chemical reaction to find it. Okay, now for luster. So we need to know that luster is supposed to be the way that a substance reflects light. That's also still a physical property. Ductility is also a physical property, the ability of a substance to be stretched into a wire. So you do need to know what ductility means. And then malleability is the ability of a substance to be hammered flat and to retain its shape. And then the state of matter that it's in is also a physical property. That is supposed to be a solid, liquid, or gas. That's also still a physical property. Then the melting point, freezing point, boiling point, condensation point, those are also still um, they're also still physical properties. They don't require a chemical reaction in order to find the melting point or boiling point. And then boiling point, condensation point, those are also physical properties still. All physical properties, we need to know that physical properties, they can be either intensive or extensive. Okay, so intensive properties, they do not depend on the amount of substance present. So meaning that it doesn't matter how much of the substance that you have, an intensive property is going to stay the same no matter what. Okay, so an example would be melting point or boiling point. It doesn't seem like it, but that is an intensive property. For example, if you have 1 cup of water versus 1 gallon of water, they actually will both boil at the same temperature. So, right, basically, no matter how much water you have, it's all going to boil at the same temperature. Or, for example, ductility, malleability, conductivity, luster, those are also, etc. Those are all intensive because, for example, no matter how much iron you have, it's all going to be the same ductility, the same conductivity, the same luster. Okay, now for extensive properties. Basically, they do change depending on how much of the substance that you have. A lot of properties are extensive. So, for example, mass is extensive, volume is extensive. Those kinds of things are easy because obviously, the more of a substance that you have, the more mass that'll have, or the greater the volume it'll have. But then also the amount of energy, whether it's kinetic or potential. Okay, so for example, like potential energy, for example, if you have a protein bar and it says one protein bar says 1 gram of carbohydrates versus another says 20 grams of carbohydrates. I think most people can, using common sense, they know that the 20 grams of carbohydrates has more energy than the 1 gram of carbohydrates. So that's an example of how potential energy is an extensive property. Okay, now let's move on to chemical properties. So chemical properties are supposed to be traits that can only be seen, right, if the substance has that property. But they're usually only seen during a chemical reaction. Okay, so, right, it's usually involving react with. Does the substance chemically react with something else? Okay, now reactive with oxygen. So basically, iron has that chemical property of being reactive with oxygen. And then silver, copper, and brass, they also have that chemical property of reacting with oxygen. Okay, then reactivity with water. That's also a chemical property. A lot of chemical properties are about reacting with, reacting with, reacting with. Then reacting with acids or bases, combustibility or flammability, those are also physical properties. Okay, let's go to a new set of notes and also look at more examples of chemical properties and then physical versus chemical changes. So for the chemical properties, right, like I said, common chemical property is reactivity. So reactive to oxygen, reactive to air, reactive to water. And right, chemical properties are not easy to observe, unlike physical properties, that they require a chemical reaction. Okay, and so, right, this is a good table that shows some of the differences between chemical properties and physical properties. And notice that chemical properties, a lot of them start with react with or does not react with, flammability, and then the physical properties are all just things that we can see. Let's look at physical versus chemical changes. So physical changes are changes that do not alter the identity of the substance, meaning that it's the same substance before and after the change. Okay, so for example, right, freezing water for ice cubes, that would be an example of a physical change. And the reason why is because, for example, like liquid water is H2O, and then ice is also still H2O. Okay, so basically it's the same substance before and after the change. Okay, then mixing oil and vinegar, that's a really important one. So if we mix oil and vinegar, um, that's actually still an example of a physical change because nothing new is chemically created at all. Nothing new is chemically created. So also keep in mind that if you're dissolving something, like if you dissolve salt in water, that's also a physical change because basically, like when you mix them together, you have salt and water. But then after you mix it, you still have salt and water. Nothing new chemically was made. Um, Also, let's see. Or yeah, those were examples of physical changes. Other examples of physical changes include a change in size. So, like if you are blowing up a balloon and then you deflate the balloon, all that's happening is just a change in the size. That's it. Okay, and then change in shape. So, right, and then the change in state, right, going like from solid to liquid to gas. That would be examples of physical changes. Okay. And then for dilutions, so we need to know that for dilutions, that's when you add water to something. So that's also still just a physical change. If you think about like if you have like a coffee concentrate and then you add water to it, it's still coffee. It was coffee before and it's still coffee after. Nothing new has changed. Okay, that's different than chemical changes. So for chemical changes, they do alter the identity of the substance, meaning that it changes into something new. So, in other words, it's an example of a chemical reaction. Right? So, for example, let's see, right, we have iron rusting, wood burning, and then copper turning to brass, baking a cake, spoil milk. Okay, so right, those are all examples of chemical changes because something chemically new is being created. Okay. Um, so actually, let's take a look at some of the signs of a chemical reaction because that could help us know when there is a chemical change. So, for example, if there's a change in color, but we're not just talking about any change in color, we're more talking about like a permanent change in color. Because obviously, if you paint something, that's a physical change. Nothing new was really created or made. Okay, so right, change in color. Yeah, like I said, permanent change in color. Change in smell. So, for example, like something rotting or decaying would be examples of chemical changes. Um, oh, here's a great example of a color change would be like a banana changing color from yellow to brown. That is a meaning that it's changing, right? A chemical reaction is occurring. Okay, and then change in smell, right? A precipitate or solid forms from mixing two liquids. And then, oh, oops, I didn't mean to click on that. Right, basically, right, if you mix two liquids and then a solid forms after that, then that's a sign of a chemical reaction. And then bubbles form from mixing substances. Okay, and then change in temperature. So that would be more like if like the reaction is releasing energy um and it's like exothermic, then that would cause an increase in temperature. Or if even the reaction is absorbing energy and it's an endothermic reaction, that could actually cause the temperature to decrease. Okay, and then all right, let's see. So those are all signs of chemical reactions, which are basically signs of a chemical change. Right, other examples of chemical changes, right, would be like soured milk, because bacteria have formed new substances in the milk. And then the Statue of Liberty, that would be an example of a chemical change. And the reason why is because the Statue of Liberty is made up of copper, and copper is supposed to be orange. So why is the Statue of Liberty green? Because the copper has chemically reacted with the air over time and it has formed a new substance called copper carbonate. Okay. Okay, now, right, common errors, right? Ice melting, water freezing, water evaporating, and then steam condensing are all examples of a state change. Okay, right, these are all physical changes and not chemical. Okay, now, Okay, let's maybe